You are moving right now, not fidgeting, not shifting in your chair. Something deeper than that. Something older. You and this room, and the ground beneath the building, and the ground beneath that, all the way down to the iron core of this planet. All of it is moving, sweeping through space at roughly 220 kilometers every second. And you are not moving in a straight line. You are orbiting. The orbit is enormous. A circle so vast that one full lap takes 225 million years. The last time you completed this journey, there were no flowers on Earth. There were no mammals. The dinosaurs had not yet begun. The world was ancient, and quiet, and strange, and you, or rather, the atoms that would one day become you, were somewhere else on the same long curve, still tracing it, still going. At the center of that orbit, there is something. You cannot see it. It does not announce itself. It sits in the dark, 26,000 light years away, behind curtains of dust so thick that no ordinary light has ever passed through them to reach your eyes. But it is there. It has always been there. For as long as the galaxy has been a galaxy, which is...
You could place it inside our solar system and still have room. The orbit of Uranus would contain it. The orbit of Saturn might. It has a radius, the radius of the region where its gravity becomes absolute, of roughly 22 million kilometers. That sounds large. A bathtub full of water has a radius of perhaps half a meter. This thing has a radius of 22 million kilometers. And yet, if you set it next to a galaxy, next to the galaxy you are inside of right now, it would vanish like a grain of salt dropped into the sea. Compressed into that space is the mass of approximately 4 million suns. 4 million. Each of those suns was once perhaps a star, or perhaps not. Perhaps the mass was gathered differently, slowly, over billions of years, from the slow infall of gas and dust and the accumulated settling of matter that had nowhere else to go. We are not entirely sure. Nobody is. The origin story is incomplete, and may remain so because the event happened before there were eyes to watch it, before there were minds to ask the question. What we know is this: the thing at the center does not move. Everything else does. The stars, the gas clouds, the spiral arms, the dark matter halo stretching for hundreds of thousands of light years in every direction. All of it.
The point is the still center of a turning world. The point is the axle of a wheel 400 billion spokes wide. The point is Sagittarius A star. You will spend some time with it tonight. There is no rush. It has been waiting for 4 billion years, more or less, which means it has a kind of patience that makes our longest nights feel brief. You can settle in. You can let your breath slow. The distance is safe. 26,000 light years is a very comfortable distance. And the dark, here on your side of that distance, is the ordinary quiet dark that has always been here. The galaxy turns slowly above you. Something enormous and ancient sits at its heart. You have been near it your whole life. Every day you have lived, you have been moving along this vast orbit, carried by a planet, around a star, around a center. You have eaten and slept and laughed and worried, and the whole time, 220 kilometers per second, silently, the galactic center has been the axis of it all. There is something settling about that, if you let yourself feel it. Not frightening. The distance is so immense, the forces here so negligible at this remove, that the black hole at the center can have no direct effect on you, on your body, on your night. It is simply the center, the axle.
the still point at the heart of a turning system that is incomprehensibly larger than anything you will ever see or touch. It is dark there at the center, darker than the space between galaxies. The dust sees to that. But in other wavelengths, in the frequencies we have learned to listen to since Jansky and his merry-go-round and his Model T wheels, the center is not silent. It speaks in radio. And that is where we begin. And tonight, gently, you are going to find out what it is.
For most of human history, nobody knew the center was there. That is not quite the same as saying nobody looked. People looked. Astronomers have been looking at the night sky with extraordinary care and patience for thousands of years. They mapped the stars with a precision that would embarrass many modern surveyors. They tracked the planets. They calculated eclipses. They built instruments out of wood and brass and glass, each one more refined than the last. Each one pointed upward at the same depthless dark, trying to learn the shape of the thing they lived inside. And still, the center hid. The reason is dust. Not the dust on your windowsill, not the dust that settles in corners and on top of bookshelves. Something older and more pervasive. Interstellar dust, microscopic grains of carbon and silicate and iron, perhaps the size of the particles in cigarette smoke, drifting between the stars in enormous, diffuse clouds. There is not very much of it in any one place. If you could take a cubic meter of the densest dust cloud and hold it in your hands, it would weigh almost nothing. The grains are spaced apart by distances that dwarf anything we would recognize as close. But space.
The center of the Milky Way is hidden behind the equivalent of 30 magnitudes of visual extinction. That number sounds technical, but here is what it means in plain terms. If the galactic center were sending a beam of ordinary light toward your eye, the dust would reduce its brightness by a factor of 1 followed by 12 zeros. It would be as if someone placed 1 trillion panes of frosted glass between you and a candle. The candle would not be dim. The candle would be gone. And so, for millennia, the center was gone. People could see the Milky Way band across the sky, that familiar pale stripe, the compressed light of 100 billion stars viewed edge on, and they knew or guessed or felt that it had a center somewhere. Early astronomers in the 20th century began to suspect that our sun was not at the middle of things. The sun felt important. It was, after all, the star that kept us alive. But the distribution of star clusters, the way the galaxy seemed to bulge toward a particular region in the direction of the constellation Sagittarius, all of it pointed away from the sun and towards something else, towards something deeper and more central, hidden behind the dust, unreachable by any telescope that worked with light. The breakthrough came not from light, but from something that dust cannot stop. Radio waves.
In the 1930s, a young engineer named Karl Jansky was hired by Bell Telephone Laboratories to investigate interference that was affecting transatlantic radio communications. Interference was a practical problem. Interference meant static and distortion in signals that people were trying to send across an ocean, and Bell wanted to know where the noise was coming from so they could reduce it. Jansky built a large antenna, a rotating structure made of wood and metal pipe, mounted on a set of wheels taken from a Model T Ford, so that it could be slowly turned to point in different directions. The neighbors called it Jansky's merry-go-round. He pointed it at the sky and listened. He found 3 sources of interference. The first was local thunderstorms. The second was distant thunderstorms. The third puzzled him. There was a hiss. A persistent, steady, gentle hiss that rose and fell with a period of roughly 24 hours. Or he eventually realized, not quite 24 hours. The period was closer to 23 hours and 56 minutes. That difference of 4 minutes is significant. It is the difference between a solar day and a sidereal day, the time it takes for a point on the sky to return to the same.
And when Jansky traced the direction, it pointed toward the constellation Sagittarius. The galaxy was making noise. Jansky published his findings in 1933. He was 36 years old. He wrote about it plainly, without drama, in the way that careful scientists tend to write about things that will later seem extraordinary. The signal, he noted, appeared to originate from the general direction of the galactic center. He did not know what was making it. He did not speculate wildly. He simply described what he had found and filed it in the record and moved on. There is something about that plainness that deserves a moment of attention. Jansky did not know he was listening to the heart of the galaxy. He was looking for noise in a telephone line. He found instead one of the most remarkable discoveries of the 20th century, wrapped in the form of a quiet, steady hiss that few people noticed at the time. The universe does not always announce its secrets with trumpets. Sometimes it offers them as a soft, persistent background sound that most people mistake for interference. The discovery was noticed. It was also, for a while, mostly ignored by astronomers. Bell was not sure what to do with it. Jansky himself was reassigned to other projects. A hobby astronomer named Grote Reber.
But the field moved slowly. There were other concerns. The world was approaching a war. It was not until after the war, after radar technology had transformed the ability to build and use radio antennas, that radio astronomy began to grow into a real discipline. Astronomers built larger dishes. They developed better receivers. They began to resolve finer and finer detail in the radio sky, distinguishing individual sources from the general background hiss. And slowly, over the following decades, the picture of the galactic center began to sharpen. There was something there, something brighter than its surroundings, something compact. Not a broad, diffuse glow, but a distinct point, or near point, of radio emission sitting at the heart of the Milky Way. Right where the old observations and the distribution of globular clusters and the bulge of the inner galaxy all agreed the center ought to be.
It was small, much smaller than the broader region of radio emission surrounding it. In the years after the discovery, subsequent observations with even higher resolution would show that it was smaller still than initially measured, and smaller again with each improvement in instrumentation. The source shrank with every new observation, not because it was actually shrinking, but because each new measurement was more accurate, and the more accurately you measured, the smaller and more point-like the source appeared. It was small. It was bright. It was right there at the center of everything. They needed to name it. The broader region of radio emission in that part of the sky had already been catalogued as Sagittarius A, named for its position in the direction of the constellation Sagittarius, and given the letter A because it was the brightest radio source in that area. The compact source that Balick and Brown had found was inside Sagittarius A,
and it was brighter still. In the naming conventions of radio astronomy, a star symbol, an asterisk, denotes something particularly intense, particularly point-like. So they called it Sagittarius A star. The name has a quiet rightness to it. A star symbol appended to the name of an Archer constellation, marking the heart of the Milky Way. There is an accidental poetry in the way the nomenclature landed. Nobody planned it.
It simply emerged from the conventions of the field, from the catalog numbers and the brightness rankings and the asterisk placed where brightness concentrated, and it stuck. Sagittarius A star, abbreviated in scientific papers as Sagittarius A star, spoken aloud in the way astronomers speak it at conferences and in lecture halls. Sagittarius A star. But what was it? The name was clear. The nature was not. In the years that followed the 1974 discovery, astronomers worked to pin down the properties of the source. One thing became quickly apparent and increasingly strange. Sagittarius A star did not move. Everything else near it moved. The stars in the inner galaxy orbited. The gas clouds swirled and streamed. The broader structures of the galactic center, the dense star-forming regions, the filaments of ionized gas, all of it showed motion. But Sagittarius A star sat still. Precisely still. When astronomers measured the proper motion of the source,
the explanation for this stillness pointed toward mass. Enormous mass. An object that is far heavier than its surroundings will appear almost stationary, while those surroundings circle it, just as the sun appears stationary while the planets orbit. Because even though everything is technically pulling on everything else, the lightweight things move more than the heavy thing does, by a factor proportional to the ratio of their masses. The stillness of Sagittarius A star suggested that it was not just massive, but vastly, overwhelmingly massive compared to everything around it. Every star and cloud that orbited it was pulling on it, gravitationally, and it barely noticed. It sat there like an anvil while dust motes swirled around it. The anvil metaphor is insufficient. An anvil is heavy because iron atoms are packed closely together. This was something else. Something that was heavy in a different, more fundamental way. Not because of the density of ordinary matter, but because of the sheer quantity of mass compressed into a region that was, by galactic standards, extraordinarily small. You can feel your way toward it intuitively, even if the mathematics is not immediately accessible. Think of a spinning record. You place it on a turntable and start the motor, and the record begins to rotate. The center of the record, the hole, the small dark circle at the exact middle, does not spin away. It stays fixed. Everything else on the record rotates around it, but the center holds its position. Now imagine that the record is 400 billion stars wide, and the center is not a hole but a mass, and the mass is 4 million times the weight of the sun. The center holds. What was it? The question would take decades to answer with confidence. The answer, when it came, required not just better telescopes, but a particular kind of patience. The patience of astronomers who were willing to watch the same patch of sky, year after year, for a generation, watching for stars, watching for the way stars move when something very dark and very heavy is standing nearby.
imagine standing in a foggy valley on a still night. The fog is thick. You cannot see across the valley. You cannot see the hills on the other side.
Everything beyond a certain distance is simply gray and soft and impenetrable. But somewhere in the fog, perhaps half a kilometer away, you begin to notice something. The fireflies are behaving oddly. They are not drifting randomly, the way fireflies do on ordinary nights. They are following curves. They are looping and arcing and sweeping in patterns that have a shape to them, an elliptical shape, a shape that implies a center. The fireflies are not orbiting each other. They are orbiting something else, something you cannot see, something in the middle of their loops, right in the thickest part of the fog. You cannot see what is there, but you can infer it. You can measure the arcs. You can track the velocities. You can apply the mathematics of orbits, mathematics that has been refined over centuries, mathematics so reliable that we use it to send spacecraft.
The fireflies were stars, real stars, hot and ancient and massive, orbiting deep in the gravitational well at the center of the Milky Way. And the invisible thing at the center of their orbits was Sagittarius A star. The work began in earnest in the early 1990s. There is a particular quality to this kind of scientific patience that is worth sitting with for a moment. Astronomers who commit to long baseline observation programs know, when they begin, that they will not see results for years, perhaps a decade, perhaps longer. They are investing time, their professional time, the limited years of their careers, in an observation that will only make sense in retrospect, once enough data has accumulated to reveal a pattern. It is not unlike planting a tree. You put the seeds of your measurement into the ground, and you water it with more measurements, and you wait, and gradually something grows that you could not have seen at the start. Two groups, working independently on opposite sides of the world, set out to do something that should have been impossible: to track individual stars near the galactic center, repeatedly, over many years, and measure how they moved. The first group was based in Europe. It was led. The second group was based in California. It was led by Andrea Ghez, an astronomer at the University of California, Los Angeles. They were competitors. They were also, in a certain sense, collaborators without knowing it, in the sense that science is always a collaboration across time and distance, with each group checking the other's work, building on each other's findings, converging on the same truth from different directions. The technical challenge they faced was daunting. The galactic center, from Earth, occupies a tiny patch of sky. The stars they needed to track were faint, deeply embedded in the dust, packed closely together in a dense stellar cluster around the central point. To resolve individual stars in that crowd, to see them as distinct points of light rather than a blur, required a combination of very large telescopes, very sensitive infrared cameras, and a technique called adaptive optics. Infrared light, like radio waves, passes more easily through dust than visible light does. Not as easily as radio, but well enough that infrared telescopes can peer through much of the veil that blocks ordinary observation. The stars near the galactic center are detectable in infrared. They can be photographed. With the right equipment, they can be photographed clearly enough to measure their positions. Adaptive optics addresses a different problem: the blurring. When starlight passes through the kilometers of air above a telescope, it is bent and scattered by air currents, producing the shimmering effect that makes stars twinkle prettily and makes precise astronomical measurements very difficult.
Adaptive optics systems use a bright reference star, or an artificial laser-created star, to measure the atmosphere's distortion in real time, and then correct for it using a flexible mirror that changes its shape hundreds of times per second, continuously compensating for the blur. The result is that a large ground-based telescope with adaptive optics can take images nearly as sharp as those from a telescope in space. Images sharp enough to resolve individual stars in the dense cluster at the galactic center. Images sharp enough to track those stars' positions from year to year with extraordinary precision. Both groups spent years building the equipment and refining the techniques. Then they pointed their telescopes at the galactic center, and they waited. They waited for the stars to move. The stars moved. Over the course of the 1990s and into the 2000s, as the observations accumulated and the baseline of measurements grew longer,
But the stars in question were not orbiting other stars. They were orbiting something dark, something at a specific, fixed point in space. Something that could not be seen in any wavelength of light, but whose presence was written into the motions of everything around it as clearly as a signature on a letter. One star in particular became the centerpiece of the story. Its catalog name is S2. In the Los Angeles group's notation, it is sometimes called S02, a small, hot, blue star, perhaps 15 times the mass of our Sun, perhaps 100 times as luminous, following an elliptical orbit around the center of the galaxy with a period of approximately 16 years. 16 years for one full orbit. In the lifetime of the ongoing observations, astronomers watched it complete more than one full revolution. The orbit of S2 is extreme by any measure. At its closest approach to the central dark point, a point called periapsis, S2 comes within roughly 1,400 astronomical units. One astronomical unit is the distance from the Earth to the Sun, so S2 comes within roughly 35 times the distance from the Sun to Pluto. In the scale of the solar system, that would still be well beyond the outermost reaches of our planetary neighborhood. But
What sits at the center of S2's orbit has a mass of approximately 4 million solar masses. The gravitational field at periapsis is correspondingly intense. At closest approach, S2 is moving at approximately 7,000 kilometers per second. 7,000 kilometers every second. The Earth moves around the Sun at roughly 30 kilometers per second, a speed that already feels impossible in any ordinary frame of reference. 7,000 is more than 200 times faster. It is approximately 2.5% of the speed of light. At that speed, S2 sweeps through the inner part of its orbit, curves sharply around the invisible mass, and then arcs back outward, slowing gradually as it climbs away from the gravitational well, heading for the far end of its 16-year journey. What does this star experience at periapsis? We cannot say with certainty. The tidal forces, the differential pull of gravity across an extended body, are significant, but not catastrophic at that distance from a 4 million solar mass object. S2 is not being torn apart. It survives its closest approach and continues on its orbit, battered perhaps, stretched perhaps slightly by the tidal field, but intact.
a star hurtling at a fraction of the speed of light around a dark point in space, the gravitational field of 4 million suns concentrated in an area smaller than our solar system, everything moving and bending and following the ancient mathematics of gravity, with a perfection that requires no witness and no approval. from the observations of S2 and the many other stars tracked in the same region. There are dozens of them, each with its own elliptical path, each contributing another line of evidence to the same picture. It became possible to calculate the mass at the center with extraordinary precision. The mass is approximately 4,100,000 solar masses, 4,100,000 times the mass of the Sun. All of it concentrated in a region that is, by the standards of 4 million suns, unimaginably compact. The question the astronomers faced was, what could it be? The obvious answer, the answer that had been suggested since at least the 1970s, when astronomers first began to understand that the centers of galaxies often harbor strange and energetic objects, was a black hole, a supermassive black hole, not a stellar mass black hole of the kind produced when a single massive star collapses at the end of its life, which might contain a few times the mass of our Sun, but something on an entirely different scale.
Something formed through processes that are still not entirely understood, over timescales that are still debated, involving the accumulation of matter in the deep gravitational center of a galaxy over billions of years. But other explanations had to be ruled out. Science does not accept the most dramatic conclusion simply because it is dramatic. It requires that the alternatives be eliminated first. Could the mass be made of dark matter? Dark matter is real. Its gravitational effects are observed throughout the universe. But dark matter does not concentrate into a point. It spreads out in diffuse halos. To accumulate 4 million solar masses in the region inferred from the stellar orbits, you would need a density of dark matter that has never been observed anywhere, and that models of dark matter cannot explain. Could it be a dense cluster of ordinary objects? Neutron stars, stellar mass black holes, dim white dwarfs, packed closely together. This was taken more seriously. But a cluster dense enough to produce the observed gravitational effect would be unstable. The close interactions between its members would cause them to scatter, to be ejected, to diffuse outward over time. On the timescales involved, billions of years, such a cluster would not survive in the compact configuration required. The mathematics of gravitational dynamics rules it out.
Not with a sudden announcement and a press conference and a moment of revelation, but with a gradual accumulation of certainty. Each new year of observations making the orbits more complete, making the mass more precise, making the alternative explanations less and less plausible. By the middle of the 2000s, the scientific community was, in effect, certain. By the 2000s and 10s, the certainty had hardened into consensus. By 2020, the Nobel Committee agreed. In October of 2020, the Nobel Prize in Physics was awarded, in part, to Reinhard Genzel and Andrea Ghez, the two group leaders who had spent decades, separately and persistently, and with extraordinary care, watching the stars near the galactic center trace their impossibly fast ellipses around a point of concentrated darkness. They shared half the prize. The other half went to Roger Penrose, a British mathematician and physicist, for his earlier theoretical work demonstrating that black holes are a necessary consequence of Einstein's general theory of relativity. The prize was.
It is the kind of journey that only science makes, not in a straight line, not quickly, not with a clear map of where it is going, but by following the evidence wherever it leads, with patience and precision and the willingness to revise. The journey led here, to a dark point in space,
26,000 light-years away, behind its curtain of dust, circled by stars moving faster than anything we encounter in our ordinary lives, sat something that has no surface, no atmosphere, no light of its own, something defined entirely by what it does to the space around it, something from which, beyond a certain boundary, nothing that has ever crossed can return. A black hole. The black hole at the heart of the Milky Way. Our black hole. The one at the center of the orbit that takes your atoms 225 million years to complete. And now the question shifts. Not just where it is, not just how much it weighs, but what is it? What does it mean, physically, for something to be a black hole? What happens to space and time in the vicinity of Sagittarius A star?
An orbit completed, and completed again, by a star that has no idea what it is circling. Only that the gravity is there, as it has always been, patient and precise, and entirely indifferent to the time it takes. The center holds, and what it is exactly, what lies at the very edge of the dark, that is where we are going next.
So we have arrived at the question. We have watched the stars move. We have traced their paths through the infrared dark, year after year, decade after decade. We have measured their speeds and mapped their curves and worked backward through the mathematics. And the mathematics have pointed, without hesitation, without ambiguity, towards something sitting at the center of our galaxy. Something that holds the mass of 4 million suns. Something that occupies a region of space smaller than the distance between us and Mercury. Something we cannot see. The question, then, is a simple one. What is it? The word we use is black hole, but the word is misleading in almost every way. It is not a hole. It is not empty. And it is not, in any meaningful sense, a place you could point to on a map and say, there, that is the thing. That is where it lives. A black hole is a condition of space itself. And because that phrase, a condition of space, sounds abstract, almost philosophical, let us take it slowly. Let us build toward it, rather than simply accept it. Because the thing at the center of our galaxy is not abstract. It is as real as anything in this universe. More real, perhaps, in the sense that its effects are measurable, and its presence undeniable. The mathematics that describe it are among the most thoroughly tested in all of science.
The black hole at the center of our galaxy is not a mystery in the sense of being unconfirmed. It is a mystery in the deeper sense, confirmed, measured, photographed, and still somehow difficult for the mind to truly hold. Let us begin with something familiar. Gravity. You know gravity. You have felt it your entire life, pulling you gently toward the earth, holding the air around you, keeping the moon in its slow circle overhead. Gravity is the tendency of mass to draw other mass toward it. The more mass you concentrate in one place, the stronger that pull becomes. Now imagine compressing mass. Compressing it further and further, denser and denser, into a smaller and smaller region of space. As you do this, the gravity at the surface of that compressed object grows stronger. The escape velocity, the speed something would need to reach in order to fly away from that surface and never return, grows higher. For the Earth, escape velocity is about 11 kilometers per second. Fast, but achievable. We have sent rockets away from Earth at that speed, and they have not come back.
The escape velocity at the surface of that object reaches a very particular threshold. It reaches the speed of light. Nothing travels faster than light. This is not a limitation of our technology. It is a feature of the universe itself. Space and time are woven together in such a way that the speed of light is the absolute ceiling. Nothing crosses it. Not information, not energy, not the faintest whisper of a quantum fluctuation. And so, when the escape velocity at a surface reaches the speed of light, something very quiet and very total happens. Nothing can leave. Not light. Not anything. The surface at which this happens, the boundary, the threshold, has a name. We call it the event horizon. And here is the first thing to understand clearly, because it matters. The event horizon is not a wall. It is not a surface you could touch. It is not made of anything. It is a mathematical boundary in space. A line of no return. A place where the geometry of the universe has folded in on itself just enough that every path forward, every direction you could travel, leads inward. Think of it this way. Imagine you are floating in a river. The river is slow at first, and you can swim.
There comes a point where even swimming as hard as you cannot make progress upstream. You can only drift forward. The event horizon is something like that boundary. The current of space-time itself is flowing inward, faster than anything can travel outward. Beyond that point, there is no upstream anymore. Inside the event horizon, according to everything we understand about physics, the collapse continues. The mass does not stop compressing. It falls inward, denser and denser, until all of it, all 4 million solar masses, in the case of Sagittarius A, is concentrated at a single mathematical point of infinite density. We call that point the singularity. The singularity is, in an honest sense, the place where our equations break. Infinite density is not something our current mathematics knows how to handle. It is the edge of our understanding. A wall that physics has not yet learned to climb. Some physicists believe the singularity is not truly infinite, that some future theory, some deeper description of gravity and quantum mechanics working together, will smooth it out into something finite but still almost unimaginably dense. But for now, the singularity is where we stop knowing, and between the singularity at the center and the event horizon at the boundary, there is something profound, a region of space.
A closed pocket of space-time, folded away from the rest of everything. Now, Sagittarius A, its event horizon, the boundary of no return, is estimated to span a diameter of roughly 24 million kilometers. That is a large number by everyday standards, but the solar system is vast. Mercury, the innermost planet, orbits the Sun at an average distance of about 57 million kilometers. So the event horizon of the black hole at the center of our galaxy would sit comfortably within Mercury's orbit. If you placed Sagittarius A at the center of our solar system, its boundary, the point of no return, would trace a circle well inside Mercury's path. The planets would all remain outside it. The Earth would remain outside it. And yet, enclosed within that boundary would be the equivalent of 4 million suns. Let that settle for a moment. 4 million suns, compressed into a volume that Mercury's orbit encircles. Most black holes we encounter in astronomy are born from individual stars. A massive star, perhaps 20 or 30 times the mass of our own sun, reaches the end of its life. Its nuclear fuel runs out. The outward pressure.
What remains is a stellar mass black hole,
typically a few times to perhaps a few dozen times the mass of the Sun, compressed into an object perhaps 30 kilometers across. These stellar black holes are extraordinary in their own right. But they are small by comparison. Sagittarius A is what we call supermassive. That word, supermassive, is doing real work. It is not just a larger version of a stellar black hole. The physics of something containing 4 million solar masses differs from the physics of something containing 10. The density at the event horizon, for instance, is actually lower for a supermassive black hole than for a stellar one. Counterintuitive but true. The event horizon is so large that the mass spread across that volume creates conditions that are, by human standards, extreme, but not infinitely so at the boundary itself. A stellar black hole's event horizon is incredibly dense, incredibly compact, with tidal forces at the boundary that would tear apart anything approaching it. At the event horizon of Sagittarius A, by contrast, the tidal forces are much gentler. Something could, in principle, cross the boundary without being shredded at the moment of crossing. How did something like Sagittarius A come to exist? This is a question astronomers are still working.
One idea is that it began as a stellar black hole, born in the violent early universe when massive stars formed and died quickly. The first generation of stars, sometimes called population 3 stars, a designation for what we have never directly observed but infer from the logic of cosmic chemistry, were enormous, far larger than any star forming today. They burned hot and fast and died young, collapsing into black holes that seeded the early universe with gravity wells. Over billions of years, those seeds grew, not smoothly, but in episodes, merging with other black holes, pulling in gas and dust and stars from the surrounding region, growing slowly during quiet times, growing dramatically during moments of intense feeding. There is also a newer and more exotic hypothesis that some supermassive black holes formed directly from enormous clouds of gas in the early universe, collapsing without the intermediate step of a stellar life cycle. Direct collapse, bypassing stars entirely. The details are still being worked out. The universe, it turns out, had more than one way to build something extraordinary. Around the black hole, there is often an accretion disk, a swirling structure of gas and dust, heated by friction and compression.
Quasar, blazars. These are distant galaxies whose central black holes are actively feeding, consuming enormous quantities of matter, radiating energy outward with a brightness that outshines entire galaxies of hundreds of billions of stars. Sagittarius A has a small, faint accretion structure. It is not eating much, not right now. We will return to that quietness later. For now, simply note that the machinery is there. The disk exists. The infalling material exists. The black hole itself, the singularity, the event horizon, the geometry of no return, exists at the center of it all. We have described it now in the language of physics. The event horizon, the singularity, the density, and the escape velocity, and the folding of spacetime. But perhaps the most honest thing to say is this. A black hole is the universe
Things so extreme that the words we use, mass, gravity,
density, boundary, wear thin at the edges and stop covering the reality. And yet the reality persists. The black hole does not need our comprehension to exist. It has been there since the galaxy was young. It held its mass when the first stars in the Milky Way ignited. It held its mass when the solar system condensed from a swirling cloud of gas and dust. It held its mass when the first living things stirred in the shallow oceans of early Earth. And it will hold its mass long after everything we consider civilization has concluded.
For most of human history, we understood the sky through light our eyes could collect. We looked up. We watched. We built better eyes, telescopes, mirrors, lenses, and we saw further and in more detail. But we always saw through light. Then, gradually, we learned that light is only a thin slice of something broader. The universe radiates in wavelengths our eyes cannot detect. Infrared, ultraviolet, X-ray, gamma ray. And at the other end of the spectrum, radio waves, long, slow oscillations that carry their own kind of information across vast distances, through dust, through gas, through the obscuring veil that hides the galactic center from our optical eyes. Radio astronomy opened a new window. The universe radiates in wavelengths that carry their own kind of information across vast distances. And at the center of our galaxy, there was something bright. The compact source we now call Sagittarius A star had been quietly radiating there all along, waiting to be found. For decades, that source was the evidence. Not an image, not a picture, just a signal. A region of the sky that emitted radio waves with a particular character, at a particular location, around which stars orbited, and from which nothing physical had ever been resolved.
A single radio dish can collect radio waves, but its resolution, its ability to distinguish fine details, is limited by its size. The larger the dish, the finer the detail you can see. A dish 100 meters across is sharper than one 10 meters across. But the resolution needed to image the shadow of Sagittarius A, a feature spanning roughly the size of Mercury's orbit at a distance of 26,000 light-years, is extraordinary, far beyond what any single dish could achieve. But there is a technique. Radio interferometry. If you take two radio dishes, separated by a long baseline, and carefully record the radio waves they each receive with precise timestamps, you can later combine those recordings mathematically. The pair of dishes behaves, in terms of resolution, as if it were one enormous dish spanning the distance between them. The Event Horizon Telescope, the EHT, took this principle and extended it across the entire planet. A network of radio telescopes spread across multiple continents and multiple mountain peaks, all pointing at the same target at the same time. Telescopes in Hawaii, in Chile, in Spain, in the American Southwest, at the South Pole, and elsewhere. Each one recording, with atomic clock precision, the radio waves.
The challenge was immense, and it is worth sitting with that for a moment before we move on. Every telescope in the network had to point at exactly the right piece of sky. The data collected at each site
had to be stamped with timing accurate to within a fraction of a nanosecond. Otherwise, the mathematical combination would not work. The data volumes were staggering. Petabytes of recordings, shipped on hard drives by plane, transported to correlation centers where supercomputers spent months combining the signals. The weather at each site had to cooperate. A cloud over the South Pole telescope during the observation run could ruin that data stream entirely. And then there is the target itself. The EHT team has described the task of imaging Sagittarius A as something like photographing a donut placed on the surface of the moon while standing on the Earth. You are looking across that staggering distance.
Unlike the larger black hole that the EHT imaged first, the one in the galaxy Messier 87, a slower and more sedate target, Sagittarius A moves. The gas swirling near its boundary changes on timescales of minutes. It flickers and shifts. The structure of the emission region evolves faster than the observation window. Imaging it was not like taking a photograph of a still subject. It was more like trying to photograph a candle flame in a breeze, using an exposure that takes hours, and then reconstructing what the flame looked like from the blur. The EHT team collected their first observations of Sagittarius A in April of 2017. Then came years of analysis. Careful, painstaking work. Different teams independently reconstructing images from the data using different methods. Different mathematical approaches, different algorithms, different assumptions, all converging, slowly, on the same result. On the 12th of May, 2022, the Event Horizon Telescope collaboration released the image. It is a small thing if you encounter it without context. A ring of warm light, orange, amber, deep gold, glowing against a field of black. The ring is not perfectly uniform. It has brighter and dimmer regions.
Let us be precise about what we are actually seeing in this image, because the image is richer than it first appears. The bright ring is not the surface of the black hole. The black hole has no surface in any ordinary sense. The bright ring is light, radio waves, in this case, that has been bent by the extreme gravity of the black hole as it passed nearby. This is gravitational lensing, a phenomenon predicted by Einstein's general theory of relativity. Mass curves spacetime, and when light travels through curved spacetime, its path bends. Near a black hole, this bending becomes extreme. Light that passes close to the event horizon gets bent dramatically, sometimes so dramatically that it curves all the way around, completing part of a circle before escaping. Light from behind the black hole, from beside the black hole, from almost every direction, gets swept up and redirected. Some of it, the light that skimmed closest to the boundary without falling in, traces a particularly tight curve and reaches us from a very specific angle. This creates what physicists call the photon ring, a bright circle of light at a specific angular radius, made up of photons that have orbited partway or even multiple times around the black hole before escaping. Inside the photon ring is
The shadow is not the event horizon itself, though the two are related in size. The shadow is slightly larger than the event horizon, roughly 2 to 3 times the event horizon's diameter, because light is being pulled in from a broader region around the hole. What you are seeing When you look at the dark center of the EHT image, is the place where light goes in and does not come out. The image is, in a meaningful sense, an image of absence, of a defined, bounded region of space from which nothing returns. And the glow around it, that warm amber ring, is the universe's light, bent and gathered, circling the drain. There is something quietly extraordinary about this moment in history. For decades, we had mathematical certainty that Sagittarius A existed. The orbital evidence was airtight. The mass calculation was solid. But a black hole that we had never directly seen was, in a philosophical sense, still a kind of inference. An extremely confident inference. But an inference. Then we saw it. Not with our eyes. Our eyes cannot detect the radio frequencies involved. Not with any single instrument of Achinchuan could have built alone. And we saw it.
A small, bright ring against a dark field, the shadow of 4 million suns. A point of no return, rendered in light. Think about what it means that the universe cooperates with this kind of scrutiny. That the laws of physics are consistent enough, and our mathematics faithful enough, that we could predict what the shadow should look like before we saw it, and then see it, and find that the prediction was right. The shadow's size matches what general relativity forecasts. The ring's brightness profile matches the models. The shadows remat. This is not a small thing. The confidence it earns us, not in any particular person or institution.
We will watch the shadow remain, constant and dark, while everything around it churns. But something about the first image, the modest, fuzzy, amber ring of the 2022 release, carries a particular weight. It was the first time. It was the moment we looked directly at a thing we had only ever inferred. And it was there. Exactly where we expected. Exactly as massive as we calculated. The quiet wonder of that is not something that resolves quickly. It stays with you if you let it. A warm ring of bent light, a dark shadow at the center, a place we have now, finally, seen. There is also something worth noting about what the image did not show, and what that absence means. The image did not show a catastrophe. It did not show violent jets erupting. It did not show a blinding inferno of infalling gas. The image showed something quiet, a gentle glow, an orderly ring, a dark center, still and bounded, for a black hole containing 4 million solar masses.
The center of our galaxy, as rendered in the most technically demanding photograph ever assembled by human science, is not an apocalypse. It is a ring of amber light around a circle of dark, and that is, in its way, exactly as beautiful as anything the universe has offered us.
Let us go somewhere together. Not in reality, not yet, not ever with any technology we will build in our lifetimes, but in imagination. In the calm, unhurried space between wakefulness and sleep, where the mind moves freely and the rules of the ordinary world relax their grip. Imagine you are drifting, slowly, at first, very slowly, heading toward the center of the galaxy. The journey there, at any speed we can reasonably imagine, would take an enormous time. 26,000 light years. In any spacecraft we have ever built, it would take millions of years. But we are not constrained by that tonight. We are simply drifting, in the way of imagination, through the quiet dark. The stars are around us. The Milky Way is a pale river above and below. The galaxy's center glows faintly, a brightness in the star field that grows, very slowly, as we approach. After a while, after a long, slow while, the galactic center fills more of our view. The star density increases. Stars closer together here, orbiting faster, some of them sweeping through arcs that curve noticeably over years. The infrared sky is warmer. There is more going on, more energy, more.
But their orbits tell a story more dramatic than any name. They loop around the galactic center in elongated ellipses, reaching extraordinary speeds at their closest approaches, decelerating as they retreat. Their paths are the signatures of what lies at the center. Their paths are, in a sense, the writing in which the black hole announces itself. And at the center of all that motion, a darkness, an absence that has weight. We are still far away. Let us drift closer. At a large distance from Sagittarius A, the effect of its gravity is present, but not overwhelming. The nearby stars feel it. Their orbits curve around it. But space out here is not dramatically different from space anywhere else. You float freely. The stars drift past. There is nothing to feel, nothing to sense, nothing to indicate that something extraordinary is nearby. You might not even know from direct sensation that a black hole of 4 million solar masses lay anywhere close. The universe gives no warning flags at this distance, no alarm, no vibration in the dark, just stars and quiet, and the stars that should be to the side appear to have shifted slightly. Their positions are not quite where geometry would predict. The gravity of the black hole is bending the light from those stars as it travels toward us. The light is taking curved paths through curved space, and so the stars appear displaced, as if seen through an imperfect lens. This effect grows as we approach. The sky becomes a kind of funhouse mirror, subtle at first, then increasingly apparent. Stars cluster toward the edges of our field of view. And now time itself begins to play its quiet trick. General relativity tells us that time does not pass at the same rate everywhere. Time runs faster far from a massive object and slower closer to one.
If someone far away were watching you drift toward the black hole, they would see your clock, your heartbeat, your breathing, every process in your body begin to slow. Not dramatically at first, but measurably. The closer you draw to the event horizon, the more your time, as measured from far away, seems to stretch and slow. Light leaving you and traveling outward becomes redder as it climbs out of the gravitational well, its energy sapped by the effort of escaping. Your image dims. Your motions elongate. To the distant observer, you are moving in slow motion through a reddening light. From your own perspective, inside your own reference frame, nothing feels slow. Your clock ticks normally. Your thoughts move at their usual pace. You notice nothing unusual about the passage of your own time. You only see the effect in the outside universe, the sky accelerating, distant events speeding up, a universe that seems to be rushing forward while you remain suspended. There is something beautiful in that asymmetry. The universe carries on. Light continues to travel. Stars continue to orbit. And you, drifting inward.
The satellites that orbit the Earth, the ones whose signals we use to navigate, tick very slightly faster than clocks on the ground because they are higher up, further from the Earth's mass. The difference is small, a handful of microseconds per day, but it is real, and real enough that engineers must correct for it, or the positioning systems would drift and become useless. Gravity changes time. This is not poetry, it is engineering. Near Sagittarius A, there is no correction that could help. The dilation is not a handful of microseconds. It is hours, days. A year of your time near the event horizon might correspond to centuries outside. You would watch the universe age around you as you drifted inward. Stars would shift in their slow stellar motions. Galaxies would inch across the sky. The universe would visibly grow older while you remained. In your own experience, only moments older. The sky around you is extraordinary now. The black hole ahead is a vast circle of absolute darkness. Not the darkness of night, which has a texture of dimness and shadow, but a mathematical darkness, a place where light does not emerge. The brightness of the surrounding universe is gathered into a ring around that darkness. Stars, nebulae, distant galaxies. Every photon that is going to reach you has been bent by the gravity ahead, curved around the black hole, gathered from every direction, and delivered to your eyes in that single luminous boundary. Behind you, the ring of light continues. You are surrounded by it. Light from ahead is lensed toward you. Light from behind is curving over the poles of the black hole to reach you. The universe is folding around you. And still, you feel nothing dramatic. The tidal forces at this scale, the difference in gravitational pull between one side of you and the other, are present but manageable. This is the nature of a supermassive black hole. Its event horizon is so large that the gradient of gravity across a human-sized object is not the catastrophic tearing force it would be near a smaller black hole. You are not being stretched toward the singularity yet. You are simply drifting, watching. The horizon is ahead, the boundary, the line that the mathematics drew. You cannot see it. There is no marker, no glow along the boundary, no line painted in space, no change in the color of the dark.
Just space
curving, folding, quietly, becoming something different from what it was before. And the only way to know you have crossed it is the mathematics, which tells you afterward, by logic alone, that the crossing has occurred. You drift across it. Nothing happens. Nothing dramatic. No flash of light. No sound. No physical sensation of crossing a barrier. One moment you are outside. The next, by the mathematics, you are inside. The event horizon has passed over you, or you through it, depending on how you think about it, without announcement. But now something has changed. It is not something you can feel. It is something the universe has decided.
And in the spirit of this journey, it is enough to note that it is there, and to look the other way for a moment. To look back. Looking back from inside the event horizon, the universe is still visible. Light from outside can still reach you inside the horizon. Photons from the rest of the universe can still fall inward past the boundary and arrive at your eyes. The universe has not vanished. You can still see it, but it has changed. The ring of light, that gathered, bent circle of the universe, has shifted. What had been a ring now begins to look like a shrinking window. The entire visible universe, all of it, is compressed into a circle that is growing smaller, receding. As you fall inward, the window to the rest of everything narrows. Stars, galaxies, the pale river of the Milky Way, the spiral arms, the sun, impossibly distant, impossibly small. All of it collapsing toward a single bright point directly behind you as the geometry curves the light tighter and tighter. And then,
There is something in this that the mind reaches for, even knowing it cannot quite grasp it. The universe we came from, the stars and the galaxies, and the billions of years of cosmic history is still there, still glowing, still evolving. But it is separated from us now, not by distance, but by the geometry of space-time itself. No message we could send would reach it. No light we could shine would escape. We are somewhere else now, inside a fold in the universe. And it is quiet here, not the quiet of an empty room or a still field at night, not the quiet of deep water or a moonless meadow, though those are quieter than most places we know. A deeper quiet than any of those. The quiet of a place that does not communicate outward. A quiet that is not the absence of sound. There is no sound to be absent, but the absence of signal. The absence of information flowing out. Whatever happens here, the universe outside will never know. That is a strange kind of aloneness, unlike any kind of aloneness we can truly experience. On Earth, even in the most isolated places, there are signals around you. The boundary has closed. What exists here stays here. Not the quiet of an empty room or a still field at night. A deeper quiet. The quiet of a place that does not communicate outward,
a quiet that is permanent and total, and in its own strange way, complete. The black hole at the center of our galaxy has held this quiet for billions of years. Whatever fell in, gas, dust, perhaps the occasional star that drifted too close, has been here, folded into the interior geometry, contributing its mass to the 4 million solar masses that the orbiting stars trace from outside. We came from outside, and we looked at it. We measured the stars swirling around it. We photographed its shadow. We traced its influence on everything nearby. And now, in imagination, we have followed something to the boundary and past it, and sat for a moment in that impossibly still interior. It is worth noting, before we drift back outward in the imagination, that this is not a frightening place in the description physics gives us. Not at the horizon, not in those first moments of crossing. The fear we associate with black holes comes from
They are patient in the way that mathematics is patient, not eager, not malicious, simply consistent. And Sagittarius A is quieter than most. It is not feeding dramatically. It is not blazing. It sits at the center of our galaxy and holds its mass and lets the stars orbit and does not make much of a fuss. Why? That is the question the next part of this journey will follow. We have seen what it is. We have seen what it looks like from outside, from the photograph, from the ring of bent light. We have imagined, quietly, what it might be to approach it, to cross its boundary, to sit in its interior silence. Now the question turns outward again. Why, when so many other galaxies harbor black holes that blaze and devour and light up their neighborhoods for billions of light years, is ours so calm, so dark, so dormant? The answer, when we find it, will say something about our place in this galaxy, about why we exist at all in this corner of the cosmos, orbiting this ordinary star, looking outward with instruments built from curiosity and mathematics and human patience. But that answer belongs to what comes next. For now,
The stars continue their orbits. The galaxy turns as it has turned for billions of years, and out here, on a small planet near one of the spiral arms, creatures made of the galaxy's own matter look inward and ask what is there, and the center answers, in the only language it knows, with gravity, with patience, with silence. That silence is not cold. It is not indifferent exactly. It is the silence of something very old and very settled. The silence of a thing that has reached its nature and does not need to announce it. The black hole at the center of our galaxy has been there through all of it, through the formation of the solar system, through the long, slow evolution of life on Earth, through everything that has ever happened on this small blue world. It did not notice any of it. It simply held its mass and let the stars orbit and remained. And we, that too is something.
There is a question that has been drifting at the edge of everything we have said tonight. If Sagittarius A is 4 million times the mass of our Sun, if it is this enormous, patient, immovable thing at the center of our galaxy, why is it so quiet? Why doesn't it roar? The answer, it turns out, is hunger, or rather the absence of it. Sagittarius A is starving, not dramatically, not in crisis, just very, very slowly,
not eating enough. Like a great old whale drifting through empty water, mouth open, finding almost nothing. To understand what it means for a black hole to be quiet, we first have to understand what a loud one sounds like. In other galaxies, some near, some impossibly far, there are black holes that are awake, truly awake. They are called active galactic nuclei. At their most extreme, they are quasars. And a quasar is almost the opposite of what we find at the center of our galaxy. A quasar feeds. It feeds constantly, voraciously, on enormous rivers of gas and dust that spiral inward from all directions. As that material falls toward the event horizon, it compresses, it heats, it glows. Not just in visible light, it blazes in X-rays, in radio waves, in ultraviolet, in wavelengths that would shred the atmosphere of
Hundreds of billions of stars, and still the center burns brighter than all of them combined. Some quasars project jets of plasma, charged particles accelerated to nearly the speed of light, out from both poles, extending for thousands of light years. These jets are visible across the universe. We can see quasars from when the cosmos was less than 1 billion years old. They were burning even then. That is what an awake black hole looks like. Sagittarius A is not that. Sagittarius A is nearly 10 billion times less luminous than what you would expect from a black hole of its mass if it were actively feeding. Astronomers have a term for this. They call it radiatively inefficient. It is a polite technical way of saying it barely eats anything at all. The material that does drift close to Sagittarius A, the thin, hot gas shed by nearby stars, the occasional wisp of dust that wanders too far inward, most of it doesn't even make it past the event horizon.
The neighborhood around Sagittarius A is not as empty as it might seem. There are thousands of stars within just a few light-years of it. Some of them are young, massive winds streaming off their surfaces in constant stellar gales. Those winds carry gas. Some of that gas does spiral inward, carried on slow currents toward the center. Astronomers have estimated how much is actually available. The supply is there, technically, but the black hole only captures a very small fraction of it. The rest disperses before it can fall in. It is as if the kitchen is almost stocked, but the door keeps swinging open, and most of the warmth escapes before anything can come to a boil. And so it sleeps, or rests, or simply waits, the way old enormous things sometimes do. But not always perfectly still. Every so often, not often, but sometimes, Sagittarius A stirs, flickers, briefly brightens, then settles back down. These are called flares. They happen in X-ray wavelengths. Sometimes in infrared. A few times each day the emission from scar A increases by a factor of a few. Sometimes by a factor of 10 or more. One particularly dramatic flare, recorded in the early 2000s, briefly made it appear 400 times brighter in X-rays than its usual sleeping state. 400 times.
Astronomers believe they happen when a small clump of gas, perhaps stripped from a passing star, perhaps a pebble of magnetic energy suddenly released, falls too close and gets torn apart. For a brief moment, the infalling material heats to extreme temperatures. It glows in high-energy light, and then it is gone, swallowed or dispersed, and the quiet returns. In 2019, a remarkable flare was observed. It was the brightest ever recorded in near-infrared.
For about 2 hours, Sagittarius A was many times brighter than any previous infrared observation had measured. Astronomers scrambled to understand it. A star named S02 had passed very close to the black hole the year before, on its elliptical orbit, stripping away some gas as it went. That gas, drifting inward for months, might have finally arrived. A delayed echo of a close encounter. Or it could have been something else entirely. These are not fully understood. These flickers and flares are the black hole's way of speaking in a language we are still learning to translate. But there are older echoes too, much older. There is evidence, written not in current observations, but in light arriving from unexpected angles. That Sagittarius A was far more active.
The clouds were glowing in X-ray light, but there was no obvious nearby X-ray source illuminating them. The light seemed to be reflecting off the clouds, but from what? When they traced the geometry, they found that the reflected light was consistent with a powerful X-ray source at the position of Sagittarius A. An outburst that would have been, in X-rays, about 1 million times more luminous than what we observe today. Not quasar bright, not earth-shattering by cosmic standards, but dramatically more active than the dim sleeper we see now. The clouds were acting like mirrors. They had caught the light from a past flare, or perhaps a sustained period of activity, and they were still glowing from it. The outburst itself had already ended, but the light was still traveling, still bouncing off distant gas, arriving at our telescopes centuries after the source had gone quiet again. This phenomenon has a name. Astronomers call it a light echo, the universe's version of a delayed photograph. So the black hole did speak once, perhaps many times, over millions of years. It has had episodes of activity, moments when more gas fell inward, when it briefly brightened, and then it settled.
And yet the light goes on traveling, bouncing off surfaces, arriving at the eyes of those who were not yet born when the original flash occurred. It is a message from a past that no longer exists, still carrying its information faithfully across the centuries. We are always, in a sense, receiving light echoes. Every star you have ever seen in the night sky is a version of its past self. The nearest one, Proxima Centauri, shows us light that left it about 4 years ago. The farthest stars visible to the naked eye sent their light thousands of years back. In a very real way, looking at the night sky is looking at a gallery of past moments, different depths of time, all arriving at once, all superimposed on a single dark field. The light echo from Sagittarius A's ancient outburst is just a more extreme version of this. The black hole spoke, or stirred, or briefly brightened, and the light from that moment is still washing through the galaxy, reflected and scattered, arriving at us now as a memory of something we did not witness directly. This is one of the stranger truths of astronomy. We can only ever observe the past. We cannot see the universe as it is right now, in this instant. We can only see it as it was. Near things, as they were moments ago. Distant things, as they.
The universe presents itself to us always in layers of time, stacked like geological strata. What we call the sky is not a single moment. It is a record. And Sagittarius A, sitting at the center of our record, has contributed its entries over billions of years. Some of those entries have already faded. Some are still arriving. And others, the ones written right now, tonight, in the quiet flicker of a dormant black hole, will not reach distant observers for thousands of years. Think about that for a moment.
The light reaching some distant galaxy from our galactic center right now. The very faint radio hiss of Sagittarius A in its sleeping state was emitted before any human civilization existed. It left before the first cities, before the first writing, before the first fields were planted. It is crossing the galaxy even now, carrying a record of our black hole's quiet present, on its way to eyes or instruments that may not exist yet on whatever worlds might someday look back at us. We are, each of us, a very brief flash. And the light from that flash goes on a long time. We are 26,000 light-years from the galactic center. That distance is an enormous buffer. Even if Sagittarius A became a full quasar, which would require an almost unimaginable delivery of material to the event horizon, its effects at our distance would be detectable, scientifically interesting, but not harmful to life on Earth. The X-ray flux might increase slightly. The galactic atmosphere might change, but it would not reach down 26,000 light-years and touch us with any violence. What we would see on a clear night is a new bright point near the center of the galaxy. Not as bright as the sun, not even as bright as the full moon, but visible. A permanent glowing ember in the direction of Sagittarius. Perhaps beautiful. But that is speculation. A thought experiment. For now, and for the foreseeable future, Sagittarius A sleeps. And there is something quietly comforting in that.
Planets have assembled and eroded. Species have risen and gone. And through all of it, Sagittarius A has been there, at the center, barely eating, barely glowing, just present. A quiet giant, a still point. Perhaps it is not so different from the way sleep works. The body quiets, the breath slows. The mind releases its grip on the day's clutter, but nothing disappears. The heart still beats. The cells still do their slow work. A kind of deep patience settles in. Things continue, just gently, just barely, just enough. Sagittarius A is not asleep in any meaningful sense. It does not experience anything. It is a region of space-time, curved past the point of return. Around 4 million solar masses compressed beyond any ordinary limit. It has no interior, no surface, no heartbeat. And yet, it is there, reliably, calmly, at the center of everything we have ever called home, in a cosmic sense. And it has been so for longer than the Earth has existed. There is something to rest against in that thought, something deeply still.
Let us pull back now, not just from Sagittarius A, but from everything we have been examining closely tonight. The orange glow of the accretion disk, the bright ring of radio waves assembled, pixel by pixel, into an image.
The Sun sits roughly 26,000 light-years from the galactic center, about halfway out from the middle to the edge of the disk. It is not in one of the main spiral arms, but in a smaller spur, a quieter stretch between the arms, sometimes called the Orion arm or the local arm. Not exactly in the thick of the crowd. A modest address in a vast neighborhood. And the sun is moving. Right now, as you lie here, in the dark, the entire solar system is moving through the galaxy at roughly 220 kilometers per second. That is not a typo. 220 kilometers every single second. Nearly 800,000 kilometers per hour. And the Earth and the Moon and you, all of it, moving together as a single unit, swept along by the gravity of the galaxy in a slow, enormous circle. How long does one full orbit take? Approximately 225 million years. Some estimates run as high as 250 million. The number varies depending on how you measure the sun's exact velocity and the exact shape of its path.
Or sometimes a cosmic year, one galactic year. 225 million trips around the sun for every planet, for every planet, for every comet, for every drifting fleck of ice in the outer reaches of the solar system. All of that, happening once, equals one galactic year. The sun is approximately 4.5 billion years old. In galactic years, that is about 20. Give or take 20 times around the galactic center. 20 full circuits of this immense, slow turning. 20 galactic years. Pause with that number for a moment. 20 laps. 20 full sweeps around the entire disk of the galaxy. Not 20 years in the sense of 20 summers and 20 winters. 20 full circuits at 220 kilometers per second, each circuit taking longer than it took for complex life to appear on Earth. The human species has existed for perhaps 1/3000th of a single galactic year. Everything that we think of as history, every empire, every invention, every human life ever lived, has happened in what amounts to a rounding error on the sun's journey.
When the sun was very young, when the earth was still a ball of molten rock, when the oceans had not yet formed, when there was no oxygen in the atmosphere, and certainly no life. The solar system was on the other side of the galaxy, a completely different orientation. If you imagine the galaxy as a clock face, and the sun is currently at 3 o'clock, then one galactic year ago, it was back at 3 o'clock, but it had completed one full trip through every hour, through 12 and 9 and 6, the whole slow sweep.
A timekeeper.
A slow, silent gravitational metronome. 400 billion stars orbit around it. Give or take. The Milky Way contains something in that neighborhood. Estimates range from 100 billion on the low end to 400 billion or more on the higher end. A large number. An incomprehensible number, really, when you sit with it. 400 billion individual suns. Each one, potentially, with its own planets. Each one completing its own slow orbit, on its own timeline, shaped by its own position in the disk. And all of them, every single one, tied to the same center. Sagittarius A doesn't command them, in any active sense. It doesn't pull with intention. It is simply the deepest point in the gravitational landscape, and so everything finds its way into orbit around it. The way water spiraling in a slow drain finds the lowest point without being directed. No mind required, just the patient geometry of mass and gravity. But the effect is a kind of order. A grand, slow circular motion that has persisted for billions of years. 400 billion stars, each in its own orbit, each sweeping its slow arc around a common center.
You are not aware of it. You cannot feel it. There is no wind. There is no vibration. There is no sensation at all associated with this motion, because everything around you, the earth, the moon, the sun, the nearest stars, is moving with you, at the same speed, in the same direction, swept along together. Motion that is perfectly shared produces no sensation of motion at all. It is like being asleep on a train. The train moves. You do not feel it. Or tonight, lying here, your body is perfectly still. And yet it is traveling at 220 kilometers per second. Both things are true at once. The stillness is real. The motion is real. They do not cancel each other out. They simply exist at different scales. This is one of the stranger gifts that science offers. The capacity to hold two seemingly contradictory truths simultaneously. At the scale of your room, you are still. At the scale of the galaxy, you are in constant motion, tracing an arc around a 4 million solar mass object at the center of a disk of 400 billion stars. Both are true at once. Probably the stillness.
You can let it go. You can let the galaxy carry you. There is something almost meditative in this image if you allow yourself to rest into it. The galaxy turns. It has always turned. It will go on turning long after any individual life, any individual planet, any individual star has completed its brief, bright arc and quieted. The turning does not require effort from anyone within it. It is simply what happens when 400 billion objects are bound together by gravity across a span of 100,000 light years. The turning is the consequence of their presence. The whole is doing something that none of the parts are consciously doing. And it does it slowly, patiently, without sound, without effort. Sagittarius A sits at the center of all of that. It does not know it is there. It does not know anything. But it does what only the densest, most massive, most gravitationally extreme objects in the universe can do. It defines a place. It marks the middle. It gives the whole galaxy a center to turn around. Without it, or without something very like it.
Part of the pattern. There are things we do not know still. Many things. We do not know exactly what happens inside the event horizon of Sagittarius A. The mathematics predict a singularity, a point of infinite density, but physicists are cautious about infinities. When a theory produces an infinity, it usually means the theory is breaking down at that scale, not that infinity actually exists in nature. Quantum gravity, a theory we do not yet have in complete form, is expected to resolve the singularity somehow, to smooth it out, to replace the infinite with something finite but very strange. What that something is, we do not yet know. We do not know exactly how Sagittarius A formed. It was probably not a single event. Large black holes likely built up over billions of years. Smaller black holes merging, stars collapsing, gas accreting slowly over cosmological time. But the details of how a 4 million solar mass object assembles itself at the center of a young galaxy.
Perhaps our galaxy is simply old enough, settled enough, that the frantic early feeding has long since subsided. Perhaps all galactic hearts grow calm with time. There is no certainty in that, but it is a thought worth holding gently. The very fact that we live in this quiet epoch, that our sun orbits a sleepy rather than a blazing center, that the galaxy around us is middle-aged and settled rather than turbulent and young, is part of why we exist at all. An early universe crowded with active quasars and frequent galactic collisions was not a hospitable place for complex chemistry, for stable planetary systems, for the long patient work of evolution. We are children of the quiet time. Our existence is, in a sense, a consequence of the black hole's sleep. The universe began in extraordinary violence, a hot, dense state of almost unimaginable energy, expanding rapidly, cooling, structuring itself into atoms, and then into stars, and then into galaxies. In its youth, the cosmos was far more turbulent than it is today. Quasars burned everywhere. Collisions between young galaxies were common. Supermassive black holes fed constantly on the abundant gas.
The pace of everything has relaxed. We live in the middle of a universe that is on a grand scale, gently winding down. Still vast, still active, still full of events beyond anything we can fully comprehend, but slower than it once was, more spread out, quieter. And at the center of our small corner of it, a 4 million solar mass object rests. In the early hours of a morning you cannot see from here. Astronomers are probably still watching it. Not because they expect anything dramatic, but because watching is what you do when something is important enough to deserve attention. The data accumulates. The understanding deepens, slowly. One observation at a time. One flare noted, recorded, added to the record. One more piece of the enormous puzzle placed carefully.
has assembled a coherent, accurate picture of a black hole 26,000 light-years away, using instruments spread across the surface of this one small world. And having understood it, at least partially, we find that it is not what we feared. It is not roaring. It is not consuming everything in its path. It is simply there, at the center, quiet and enormous and very old. And we can, if we want to, find that peaceful. And you have been looking tonight, in your own way. You have let your mind rest inside the strange, enormous, slow reality of what sits at the center of our galaxy. The star orbits, the orange ring of hot gas, the radio image assembled from a planet-wide array, the light echoes, the quiet flares, the 20 galactic years of the sun's long journey, the 400 billion stars, each tracing its own arc, all of them anchored to the same still center. And your body lying here, motionless in the dark, moving at 220 kilometers per second. Both. The galaxy does not need you to be awake to keep turning. It does not need anyone to keep turning. It will do.
The spiral arms will sweep through space, slowly, carrying their cargo of dust and gas and light. And you are a part of it, an unreasonably small part by any physical measure. One creature on one planet, around one middling star, in one of 4 spiral arms of one galaxy among 2 trillion galaxies in the observable universe. And also, somehow, the part that noticed. The part that built instruments sensitive enough to detect the wobble of stars orbiting something it could not directly see. The part that linked telescopes across the entire Earth to assemble a single image. The part that named it Sagittarius A star and studied its flares and traced its light echoes and calculated the mass of the darkness at the center. The universe produced something, eventually, that could look back at itself. That seems worth noting quietly, not triumphantly. Just gently. As a fact. As one more strange and beautiful consequence of 14 billion years of matter organizing itself in increasingly complex ways. You are a consequence of 14 billion years of the universe arranging itself. Stars had to.
The breath moves out. The body is warm. The mind is finally beginning to let go of the shapes of the day, the textures of worry and planning that fill the waking hours. They are loosening. The thoughts are getting slower, less distinct. They drift a little at the edges, the way a cloud loses its defined shape in a warm afternoon sky. Let them drift. There is nothing you need to hold on to right now. The black hole is not asking anything of you. The galaxy is not asking anything of you. The 400 billion stars are going about their long, slow business entirely without your assistance, as they have been doing for billions of years, and as they will continue to do long after your particular arrangement of atoms has quieted and dispersed and rejoined the larger swirl. That is not a sad thought. It is a settling one. Every atom in your body has been part of this galaxy for far longer than it has been part of you. The carbon in your cells was forged in the interior of a star that died billions of years ago. The iron in your blood traces back to a supernova, an explosion so violent it briefly outshone an entire galaxy. And then that material drifted through space.
You are galactic material,
briefly organized into something that breathes and thinks and looks up at the sky. And when this particular organization dissolves, as all organizations eventually do, those atoms will not disappear. They will return to the larger cycle. They will drift. They will cool. Some of them will eventually find their way into new stars. Some will fall into the orbits of new planets. Some fraction, impossibly small but non-zero, may eventually drift close enough to Sagittarius A to spiral, over millions of years, inward. Nothing is lost. Not really. Things change form, change scale, change location. But the matter persists. Nothing is lost.
You can simply be still and let it carry you.